In chapter 9, we will be looking at addition reactions, but in this case, we're not looking at addition reactions to carbon-carbon double bonds, but now we're looking at addition reactions to the carbonyl compound. You will recall that the carbonyl group is a carbon-oxygen double bond. So in this lecture, we will discuss different addition reactions involving the carbonyl functionality along with the mechanisms. So we'll do quite a bit of mechanisms in this lecture here. So more specifically, we'll look at the general mechanism for the addition reaction involving carbonyl compounds. And then we look more specific at the addition of HCl, the specific addition of water to carbonyls, the specific addition of alcohols to carbonyls, and lastly we look at the specific addition of a new type compound that we'll introduce that's called a Ylides. And the reaction is called the Wittig reaction, but we'll get into that later. First, let us look at the carbonyl compound, or the carbonyl functionality. Here it is. It's a carbon bonded to an oxygen with a double bond. As you know from the Lewis dot structure, there's an unshared pair of electrons or two unshared pairs of electrons on the oxygen, and we can draw resonance structures to show that this carbon here is positive. Of course, as you know, this bond here is described as a covalent bond, and to be more specific, it's a polar covalent bond. Two poles, a negative and a positive, or a partial negative here and a partial positive here. So the carbonyl functionality is a polarized bond where the carbon is partial positive and the oxygen, being more electronegative, is partial negative. That makes it easy in terms of addition reactions because, as we have seen before, an electrophile will add to the nucleophilic end of the molecule. So there's no debate where this E plus or H plus will add. You may recall, if it were a double bond of equal electronegativity bonded to two carbons, then we'll have to invoke the Markovnikov and anti-Markovnikov addition. But in this case, we do not have to invoke that because we know that E plus will be attracted to the electronegative oxygen to form this carbocation here. Of course, as you know, you cannot just have E plus by itself. It's balanced with a another component, which is described as a nucleophile, a negative, an anion, and the negative here, the electrons, will add to this carbon. So there's no question. So this will be the addition type product. We say it's regiospecific because the electrophile adds to a specific region of the carbonyl functionality, and the nucleophile adds to a specific region. So therefore, these type reactions are called regiospecific reactions. In the presence of an excess of nucleophile, such as a base, the nucleophile will add first to the electrophilic carbon, compared to the last one where the electrophile added first to the electronegative oxygen because it was an excess of E plus. But here we have an excess of nucleophile, so it adds first to give this type intermediate. Notice it's an anion this time and not a cation as before. Next, the E plus, which is in a concentration a little less than the nucleophile will add to the oxygen, which is negative, to form the product. Notice it's the same product, but the mechanism is different based on the excess of electrophile, E plus, H plus, or nucleophile, the negative. So the overall reaction looks like this. You have your carbonyl compound. Here's a carbonyl, polarized bond. And we have our reagent, E plus and Nu negative. Of course, that is the generic form. But if you had specific molecules, you will have to determine the E plus and the Nu negative. So since these reactions are regiospecific, we know the E plus will add here and the Nu negative will add here to give this type product as the final product. Here's an example. So benzaldehyde has this functional group right here, the carbonyl functional group, a polarized carbon-oxygen double bond. The reaction with HCN, we know this H here is the electrophile, or H plus, partial positive, and we know that the Cn here is the negative, so H plus will add over here, and the Cn will add to that carbon. So that's how you can predict the product. What you'll discover is they're typically catalyzed. So here we have a catalyst here of NaCN, so we have an excess of Cn minus. So this is going to add first to the carbonyl, and then the H plus will add next to get the same product here as the final product. Okay, let's get into some specific reactions here. And this is the addition of water to carbonyl compounds. So here it's an example, propanal, that's an aldehyde, and we're adding water to that aldehyde. It's acid catalyzed. Notice it's acid catalyzed, which means that there is an excess of H plus. The electrophile here is H plus, so therefore there's an excess. If there is an excess of H plus, the first step in the mechanism is that these electrons will bond to the H plus, negative and positive. Notice the mechanism. We're using arrows here to indicate the electron movement to bond to H plus. Here's the new bond, and here's the formal charge. So whenever we ask you to write a mechanism, use arrows to indicate electron movement and include the formal charge on the intermediate. So this is an intermediate. In the next step of the reaction, there is water that's present. Water has a pair of electrons, but it has two pairs, but one pair can be used to bond now to the electrophilic carbon. And so here is that new bond that's formed, and here's the water molecule, which has a formal charge of +1. That's an intermediate. It's called a tetrahedral intermediate. Not the product because it is charged. We can lose this proton here by taking these electrons as the arrow indicates here and bond and put it on the oxygen here to get back our neutral molecule and generate H plus again. So that is why it's called acid catalyzed, because H plus is used in the first step, but it is generated in the final step. As you may recall from Gen Chem, a catalyst is a reagent that is used but not consumed in a reaction. So it's used here and it's generated back over here. The product here is called a hydrate. So it's a hydrate of the aldehyde. So this is the product here of an aldehyde in water and a trace of acid. And this is the mechanism. Let us see how we can use the mechanism to better understand certain outcomes here. So let us look at this molecule. So here's a carbonyl, and it has very bulky groups around the carbonyl. So on this alpha carbon here, there are 3 methyl groups. Same here, 3 methyl groups. So let's look at the mechanism. These electrons here will bond to the electrophile, H+, to generate this intermediate, this charged intermediate. In the next step, a pair of electrons from water adds to the electrophilic carbon to generate the tetrahedral intermediate. Let's look at this intermediate and see if we can determine the relative stability. This carbon here is now sp3 carbon. Of course, as you know, the bond angle about an sp3 carbon, the ideal bond angle is 109.5. But because it's very crowded, based on these very bulky groups, this bond angle here is strained. So this intermediate is not very stable. It will give the product, but this molecule here is not very reactive because of the bulkiness of the groups around it, or we could say because the tetrahedral intermediate is not stable. So we can make a comparison. So this molecule here, which has bulky groups around the carbonyl, compared to this molecule which just has a methyl group bonded to the carbons of the carbonyl carbon, this molecule is now more reactive towards hydration compared to this molecule which is less reactive. So hope you can see why we insist that students have an understanding of reaction mechanisms. Because to explain certain outcomes, to explain certain observations, we will have to get to the mechanism and actually utilize the mechanism to explain some of these outcomes. So, conclusion, this molecule here is less reactive than this molecule because this molecule is more crowded around the carbonyl group compared to this molecule. Let us look at another aspect. A molecule that has electronegative atoms that's bonded to the carbonyl carbon. So this has a very electronegative fluorine. In fact, 2 fluorine atoms bonded to this carbon. Compared to this carbonyl carbon that has hydrogen that's not electronegative, in fact electropositive, in fact 2. So which is more reactive? As you can imagine, the fluorine being electronegative, it's pulling the electrons towards itself. By definition, electronegativity means the attraction of electrons towards that atom. So this carbon here, as you can imagine, would be very, very electropositive compared, of course, to this carbon. So we would expect that this molecule here is a lot more reactive, very reactive towards hydration compared to this molecule which does not contain electronegative atoms bonded to that carbon. So again, you should be able to predict the reactivities of carbonyl compounds based on their structure and also based on knowledge of the mechanisms. Let us look at another example here. Here's an aldehyde. Of course, an aldehyde because it has an H. But this has a fluorine that's close to the carbonyl, And this has a fluorine here that's further from the carbonyl. So the question now is, which would you expect to be more reactive? It all depends on how electrophilic is this carbon or these carbons. This is more electrophilic because this electronegative atom is pulling the electrons towards the fluorine that is close to it. This is not as electrophilic because the fluorine atom is further from that electrophilic carbon. So therefore we'd expect this molecule here to be less reactive compared to this molecule that has the fluorine closer to the carbonyl carbon to be more reactive towards hydration. Let us turn our attention now to the reaction of alcohols to carbonyl compounds. So now we're looking at the reaction of alcohols and not water. Of course, as you know, the structure of alcohols and water are very similar, except one of the hydrogens of water is replaced with an alkyl group. So let's look at the acid catalyzed addition of methanol to the same molecule, propanol. It's acid catalyzed, so we'd expect the first step of the mechanism to be these electrons bonding to this hydrogen to form this bond here. No, to form this bond right. Yeah, to form this bond here. And this carbon is electrophilic, so we know we have electrons here from the methanol reacting with this carbon here to form this bond in this case, this bond in this case. This is an intermediate called a tetrahedral intermediate, not the product because it is charged. We can lose this H as a proton as shown with this arrow right here. Notice the movement of electrons are indicated using arrows. And this is our product. Notice the product this time is not called a hydrate, but it's called a hemiacetal. Acetal because it's coming from an aldehyde. We'll see later on that it's a ketone, it's called a ketal. So this is a hemi or half, as we'll see in a second, of the acetal. So it's a hemiacetal of the aldehyde. Okay. Let us look at an intramolecular hemiacetal formation. And this is of practical importance because this molecule here is glucose. As you notice, it has an aldehyde functionality right here, and it has a bunch of alcohols. So in the presence of an acid, just takes a trace amount of acid, one of these alcohols here will react with the carbonyl carbon to form a hemiacetal. In this case, it would be a cyclic or intramolecular hemiacetal formation. As we know in chemistry, the six-membered ring is a very stable system. So we'll have this oxygen here reacting with this electrophilic carbon. So here is this oxygen here, and here is this carbonyl carbon right here, and this is of course the hemiacetal, and that's the cyclic form. And as you know from biology, in solution, D-glucose or glucose exists in this form in water. The hemiacetal form, also known as the glucoparanose. Okay, let us look at adding a second mole of water to the hemiacetal. So here's the hemiacetal that we formed earlier, adding 1 mole of water in the presence of an acid because it's acid catalyzed again. These electrons can add to this proton, and here it is right here, and it's charged. Now water is a good leaving group, so we can use these electrons here to put 2 electrons on our oxygen to get it to go as water, and what's left behind on this carbon is of course a positive charge. Notice this is now resonance stabilized because we can draw a resonance structure as shown here to form another resonance structure. So that shows that it's pretty stable. But the bottom line is that this carbon here is electrophilic. Same here. So in the presence of another mole of methanol, or a mole of methanol in this case, these electrons can add to this carbon here, and here's that new bond. And of course, this is an intermediate. We can lose the proton here as shown, and here we have the acetal. So now you know why the previous one here is called a hemiacetal, because it's just 1 mole of the alcohol, and the acetal now has 2 moles of alcohol. So that's called an acetal. So in the presence of 2 moles of alcohol, we can get an aldehyde to go all the way to the acetal. Notice that they're all reversible reactions, so we can go in either direction depending on the concentration of the alcohol. You may remember that from your Gen Chem called the Le Chatelier's principle. Increasing the concentration of the reaction, of the reactants, pushes the reaction to the right. And of course, if you decrease the concentration of the products, it tends to go to the right also, or we can reverse it by adding concentration of the products. Let us look at a practical application of the formation of acetals. So let us say your first task as a chemist is to carry out this reaction. So your starting material is this. Notice it has an aldehyde here. But what you really want is to carry out reactions on this end of the molecule. So this molecule is a difunctional molecule. It has a bromide, which is a good leaving group, and it is also an aldehyde. So your job is to carry out reactions here to get a functionality looking like this, but not affecting the aldehyde functionality. So what's required is to protect this group, carry out the reactions over here, and then when that's done, to regenerate our aldehyde. So we call this procedure here protection of the aldehyde group. We can protect the aldehyde group by reacting it with ethylene glycol. Notice it's a diol, so we have 1, 2 OHs on the same molecule. So if you have 2 OHs, one will go in and the other one will go in, and of course you get water as the product. So now we have our protected aldehyde. So this is an aldehyde that's protected using ethylene glycol. So now we're set to carry out reactions on this end of the molecule. So here we go. So we now have our protected aldehyde. We can carry out reactions on this end of the molecule to get that. Notice the reaction does not occur here because it is protected. Once we have carried out the reactions over here, we can move the protection as shown here. So you remove the protection in an excess of acid and water. So we are reversing the equilibrium that we looked at earlier to regenerate our aldehyde and of course our ethylene glycol as product. So this becomes our target molecule where we have carried out reaction on one end of the molecule without affecting the other end of the molecule. This is done quite a lot in industry, especially in the pharmaceutical industry, because we need a particular functionality to be maintained, but we also need to transform another region of the molecule into a different functionality. So we'll use this strategy quite a bit in synthesis. Let us turn our attention now to look at another type addition, another addition of another type reagent. This type reagent is called a Ylides. So Ylides by definition is a compound where the carbon is bonded to a heteroatom and the carbon has a charge, typically a negative charge. So if it's bonded to the heteroatom here, phosphorus, and here's a carbon, the carbon has a negative charge, as you can see here, and the phosphorus has a positive charge, and that's called a Ylide. To be more specific, it's called as phosphorus Ylide because of the presence of the phosphorus. We can of course draw a resonance structure to get this, but the bottom line is that this carbon here is nucleophilic and this phosphorus here is electrophilic. With that in mind, we can add the Ylide to a carbonyl compound in a regiospecific manner. Because we know the carbon of the carbonyl is positive, we know the oxygen of the carbonyl is negative, we know the carbon of the Ylide is negative, and we know the phosphorus of the Ylide is positive. So therefore, as shown here, a reaction can occur to generate this type species. It is not stable. It will quickly fall apart as shown here to generate here a alkene and a phosphine oxide. So the key is, let us analyze the key here. The key is we have transformed this carbonyl compound here into an alkene, where this carbon here shown in red is right here, and this carbon in black comes from the Ylide. So think about that for a while. You may even want to pause the video here and just think about that. How do we make this alkene? This alkene can be made from a carbonyl and a Ylide. Okay, let's see if we can apply that chemistry. So here we have our carbonyl, here's the carbonyl, and here is the Ylide. We know the phosphorus will add here, and the carbon will add here to form the four-membered ring that falls apart to form here the alkene. And of course the triphenyl phosphine oxide. But the key here is we have transformed here a ketone into a alkene, and notice the groups that's added. This red is coming from this region of the Ylide. Let's look at synthesis of another molecule. Now let's try to put on two H's here. That means that the Ylide here must have two H's on the Ylide. The same carbonyl here, cyclohexanone. So now we have made this type molecule. So you can anticipate what's coming for synthesis. How do you make molecules of this type, alkenes? Here's the last example. Carbonyl, ketone, and we're trying to make this type molecule here. So here's our double bond. So here would be the carbon of the carbonyl, and this would come from the Ylide. So the next step is, how do we make the Ylides? Because you cannot go to the stock room and buy the Ylides. Some you can, but a lot of times you'd have to make it. So let's see how we make our Ylides, the synthesis of the Ylides. What you can get fairly cheaply is the triphenylphosphine. Here it is. You can go to the stock room and you can buy 10 grams of triphenylphosphine fairly cheaply. You can also get here your alkyl bromide. So in a substitution reaction, as you can see here, a pair of electrons, it can substitute for the bromine. And what you have here is the Ylides salt. The Ylides salt. So that's a substitution of this portion, or this molecule, for the bromine, as you can see here. In the next step, which is an acid-base reaction, a very strong base, butyl lithium, abstracts this as a proton, leaving behind these electrons right here. So this is our Ylide. So that's how you make your Ylide. So now you can see you can make different Ylides with different groups right here, depending on the starting material. Okay, let's see if we can apply that. So let us say you're using the Wittig reaction. That's called the Wittig, based on the chemist who discovered this reaction. I think it's a German name, so it's pronounced as Wittig. So let's say you started out with this as a starting material, and your target material is this. So based on the strategy here that I'm recommended is look at your target material, identify the functional group. It is a carbon-carbon double bond. We know that we can make carbon-carbon double bonds from a Ylide and a carbonyl. So all we have to do is to identify the Ylide portion and the carbonyl portion and put them together. So the next step here shows that if you had this as your starting material, cyclohexanone, and you had this as your Ylide, putting them together, you have made your target molecule. What I should point out here, however, is that sometimes you'll have to make the Ylide, as I pointed out earlier. So let us see how we can make the Ylide and incorporate that in the synthesis of the same target molecule. So in this case, let us start with this as the starting material. So we react this, substitution of this with the triphenylphosphine to form the Ylide salt. So you may want to go back and look at that Ylide salt. The next reaction is using a strong base such as butyl lithium to form the Ylide. Once you form the Ylide, you can now react it with the cyclohexanone, which is this portion right here, to get your target molecule. So again, you can see that the application of these reactions are getting a little more involved. So you'll have to think carefully, and it is our hope that if you're asked to make a molecule, each student will come up with different ways of making it based on different strategies. So again, you will have to start analyzing your target molecule carefully, coming up with a strategy how best to make it, and then decide on what type reactions you'll have to use, and then the type reagents. So continue studying hard. I think this is the last slide. Yes, it is. So continue studying hard. We'll have a quiz on Thursday on Chapter 9, the first few sections on Chapter 9. So I'll post this. This will be, of course, online along with the PowerPoints. So take your time and work through these slides. Also read your book carefully. Design ways of synthesizing these molecules, target molecules, and it should not be too difficult once you have figured out that strategy. So hang in there. We're almost there. We are past halfway the semester. Just keep studying hard, and we'll make it. Okay.